Welcome to a new video which focuses on perception. Today, we are exploring how agents see and understand the world around them. We are diving into a file classified as Project Aegis to investigate the architecture that connects abstract reasoning to concrete reality. Modern large language models are incredibly powerful brains. They can reason through complex logic, and they can write code, and they can create elaborate plans. However, without a perception stack, these models are essentially locked in a black box. They are like a brilliant scientist sitting in a dark room with no windows and no way to interact with the outside world. This presentation will show you how we break that box open. We'll look at how an agent moves from being a static reasoning engine to becoming an active investigator in a dynamic environment. Perception is the critical system that feeds the brain the data it needs to make smart decisions. Throughout the series of slides, we will uncover the engineering pattern that allow these digital detectives to observe their surroundings and interpret signals and ultimately make sense of a chaotic digital city. Let us consider the Blindfold Protocol to understand why perception is so vital. Imagine we drop you into a completely new city, but we put a blindfold on you. You still have your goals like finding a specific suspect or getting to a local hotel, and you still have the ability to use language and logic. However, without sight, you cannot plan a route or avoid obstacles. You are effectively disconnected from the world around you. This is exactly what happens to an agent without a perception system. The agent might have a very high IQ, but if it has no sensory input, it cannot function. It cannot see the street, it cannot read the system logs, and it cannot hear the responses from an API. This is why we say the perception stack is the bridge. It connects the brain, which is the large language model, to the city, which represents the environment. Without this bridge, every piece of reasoning is purely theoretical. The perception stack turns a runtime error into a successful operation by providing the necessary context. We need to move beyond raw intelligence and focus on the inputs that make that intelligence useful in the real world. The perception stack is built on an investigative loop that moves from raw insights to structured observation, and then to meaning, and finally to a stable world state. Think of this like a detective working on a case. First, we have the sensors, which are responsible for ingestion. These are the eyes and ears of the system, where raw text and pixels and data streams enter the agent. Second, we move to the semantics, which is the deduction phase. This is the part of the process where we turn bits of information into entities and intents and logical forms. This is the true understanding phase where the agent figures out what is happening. Third, we reach the state, which is the world model. This acts as the memory of the agent. It involves building a stable and consistent picture of the city so that agent can reason over it across different time steps. By following this loop, the agent can extract the truth from a messy environment. We transition from a camera and a microphone to a magnifying glass that finds meanings, and finally to a case file that records everything. This architecture ensures that the agent is not just reaching to a random noise, but is actually building knowledge. Layer 1 of our stack consists of sensors, which we call as the informants. When we move beyond a simple chat box application, we realize that a prompt is not enough. Real agents need multiple types of informants to provide context. First, we have the textual streams. These include logs and Slack threads and various support tickets. These are human readable, but they can be very noisy and hard to parse. Second, we have visual data such as screenshots and graphical user interfaces and plots. This requires encoders to turn pixels into tokens that the model can understand. Third, We have structured data like SQL results and JSON API and telemetry. This is machine friendly, but the volume can be overwhelming for a single context window. Finally, we have physical or tool sensors, which include things like GPS or Internet of Things devices. We also use active perception, where the agent probes the environment to get more data. The goal of this layer is to create adapters. These adapters turn raw environmental signals into machine usable observations. By collecting these diverse signals, the agent gets a full picture of its surroundings rather than a narrow view from a single input source. Data ingestion is often called the cleaning the streets because it involves preparing raw data for the agent to use. Technical notes on text ingestion and retrieval, augmented generation are crucial here. Because of the limits of context window, we cannot feed the agent every single file at once. Instead, we index chunks of data for retrieval on demand. Perception includes what the agent can find when it needs it rather than just what it sees immediately. The process involves four key steps. First, we normalize the data to unify its shapes and metadata such as timestamps and sources. Second, we chunk the data by splitting long inputs to fit into context windows. Third, we filter the information to discard relevant noise that would waste processing power. Finally, we label the data by tagging it with coarse labels like error log or user query. This creates a pipeline where messy data enters a funnel and comes out as organized boxes on a conveyor belt. This organized stream allows the agent to maintain a high level of efficiency because it only interacts with the most relevant and high quality information during its reasoning cycle. Visual sensors allows the agent to move from pixel to truth, and there are three primary methods to achieve this. Method 1 is the cybernetic eye, which uses a multimodal large language model. You feed images directly into the model, which provides strong reasoning capabilities but requires expensive compute resources. Method 2 is the assistant, which uses visual encoders. In this step, a separate vision model generates text description of what it sees. For example, it might list the button on a screen or describe an error. This is a cheaper and more modular approach, but there is a potential loss of fine detail. Method 3 is the structure method, which is best for web agents. This uses accessibility trees like the HTML document model to represent UI element in a logical hierarchy. Instead of looking at a picture, the agent reads the code that builds the picture. Each method has its own strengths and weaknesses. Engineers must choose the right vision strategy based on the specific need of the agent and the available budget. By using these visual sensors, the agent can navigate complex graphical interfaces just as easily as it passes a text file. Structured data and wiretap represents a unique challenge for agents due to semantics and volume. Structured data like SQL tables and system metrics is easy for machine to read, but it is hard for an agent to digest because of its sheer size. We cannot simply dump an entire database into a prompt. Our ingestion strategy involves mapping raw fields to domain concepts. For example, we might map a user ID to a concept of a customer to help the agent understand the context. We also pre-compute views, such as aggregates and windows, rather than providing raw tables. This makes the data much more manageable. Furthermore, perception is not passive in its layer. The agent uses tools to probe the environment in a process called active sensing. An agent might perform an action like a GET request to a metrics endpoint for latency. The resulting JSON response then becomes part of the agent context for the next step. This interactive approach allows the agent to act as a digital wiretap, listening to the heartbeat of a system and extracting exactly the information it needs to solve a specific problem without being drowned in the data. Layer 2 is semantics, which we call as the deduction phase. This is where we move from a simple observation to actual meaning. Large language models shine here because they can turn raw observations into executable semantics. We can break this down into four levels of understanding. Level 1 is the lexical or surface level. These are raw tokens such as sentence saying the checkout page is broken. Level 2 is shallow semantics, which involves entity extraction. Here the agent identifies that the entity is checkout and its status is broken. Level 3 is deep semantics, which deals with intents and implications. The agent realizes that the customer cannot pay and there is a high business impact. Level 4 is executable semantics, which leads to action. The agent generates a logical step like a SQL query to select logs where the service is checkout. This process is like a detective building an evidence board. You start with a question and a picture of a server and a 404 error note. By connecting these pieces with logical string, the agent deduces that there is a widespread outage. This transforms a simple observation into a deep understanding that can drive a complex resolution. The parser is responsible for decoding the message and making sense of the world. In this context, the large language model acts as a semantic parser. It converts natural language from a user into a structured representation like SQL or API calls or domain specific languages. To improve accuracy, we use a technique called RASP, which stands for Retrieval Augmented Semantic Parsing. This involves retrieving relevant schemas or past example to help the model. The large language model uses these clues to map ambiguous languages from a user to a precise machine logic. For example, if a user says, find broken servers, that agent need to translate that into a formal query like select star where status is down. This is a crucial bridge between the language humans use and the actions machine take. By providing the model with the right structural clues, we ensure that it does not guess, but instead follows a precise technical path. This decoding process is what allows an agent to be an effective interface between a human manager and a complex technological infrastructure. It turns a vague request into a specific and actionable plan that can be executed with high confidence. Multimodal semantics is about reading the room and solving the problem of hallucination in visual tasks. When agents try to navigate a graphical interface, they often struggle with precision. The solution is a technique called set of mark prompting. This involves annotating key regions or elements on a screenshot with numerical IDs. We then feed these annotated images to a large language model. The result is a much more fine-grained perception. For example, the agent can now confidently say click button 3 rather than guessing where the button is. This significantly reduces errors during navigation. To achieve complete GUI understanding, we merge the visual screenshot with the accessibility tree from the document object model. This gives the agent a complete semantic map of the environment. Imagine an agent looking at a desk with a computer and a lamp and a door. By tagging each object with a blue box and a number, the agent can reason about the physical or digital space with much higher accuracy. This combination of visual cues and logical structure allows the agent to interact with complex environments without getting lost or making any costly mistakes. Layer 3 is a state, which we call the case file. This layer addresses the amnesia problem. If you remove the blindfold from an agent, but you take away its memory, every single glance it takes is an isolated frame. The agent would have no idea what it saw a second ago. We need a state for three main reasons. First, the agent cannot track long-running tasks without a persistent record. Second, it cannot reconcile conflicting observation that happens at different times. Third, it cannot reason about hypothetical scenarios like what if I perform action X. The solution is an internal model of the environment that persists across many time steps. This is visualized here as a detective looking at a stack of files with a bright light. Without a stable case file, the detective is just looking at random papers. By building an internal representation, the agent can connect the dots over the time. It can remember that it tried to restart a service 5 minutes ago and it failed. The historical context is what allows for complex problem solving. State turns a series of snapshots into a coherent narrative that the agent can use to navigate the future. The anatomy of a world model is essential for high level planning. We define a world model as an internal representation used to simulate the external world. There are three key components to this anatomy. First is the vision component denoted here as V. This encodes raw observation into a latent space. Second is the memory component denoted as M. This component predicts the next state of the environment given the current state and a proposed action. Third is the decoder component. This reconstructs reality from the internal model or predicts potential rewards for different actions. This capability is extremely powerful because it allows the agent to dream multiple hypothetical futures without even taking any action. Think of a detective sitting at a desk recording reality in a case file while simultaneously simulating the future in his mind. He might imagine kicking down a door and think about what would happen next. This internal simulation is the heart of effective planning. By dreaming of different possibilities, the agent can choose the path that is the most likely to lead to successful outcome. This moves the agent from simple reaction to proactive and strategic behavior based on its understanding of cause and effect. The synthesis of everything we have discussed is the sense understood model act loop. This is a continuous cycle that defines how an autonomous agent operates. It begins with the ingest phase where we turn raw signals into normalized data. Then we move to the interpret phase where we use large language models to extract meaning and intent from that data. The third step is the update phase where the agent modifies its internal world model based on the new understanding. Finally, we reach the act phase where the agent uses its model to plan the next move. This cycle then repeats as the action creates a new state in the environment which leads to a new observation. This loop proves that perception is not a passive activity. It is the very foundation of autonomy. Without a strong loop, an agent would be static and unable to adapt. By constantly sensing and understanding and modeling, the agent can navigate complex and shifting landscapes. It becomes a proactive participant in the world rather than a simple tool. This synthesis is what allows us as to build agents that can handle real-world complexity with a high degree of independence and reliability. We conclude with a debrief on the SRE agent case study. This scenario involves a production site reliability engineering agent. Its sensors are designed to pull structured alerts and read text-based logs and fetch visual dashboard screenshots. The semantic phase involves classifying the severity of an incident and extracting the impacted services. The state of the agent maintains a running list of active incidents and the mitigation that have already been tried. During your interview prep, you should be ready to discuss key trade-offs. Consider the cost versus the latency of using a multimodal large language models compared to simple encoders. Think about the depth of semantics needed for the task and whether you should use symbolic or latent storage for world model. The final note to remember is that an agent actions are only as safe as its world model is accurate. If the agent perceives the world incorrectly, it will make dangerous decisions. The case study brings together all the concepts of perception and semantics and state. It shows how we build practical and safe and effective agents for high stakes environment. This concludes our briefing on Project Aegis and the architecture of perception. Thank you for your time. If you like this video, please do share and subscribe. Thank you.